Hello, everyone. As I look into the crowd, I see some familiar faces. Some of you are active with the Apex community. Some of you have been using DataTorrent, are customers of DataTorrent, and others probably here to learn about Apex. I thank you all for being here. So I'll build on what Eric and Amol talked about. So Eric talked about the evolution of streaming and why it's important, and Amol talked about the tenets of a good streaming platform, right, or a good big data platform. So let's start with where Apex and DataTorrent fit in the big data ecosystem. So typically, you have your various kinds of data sources. They could be streaming sources, like message queues like Kafka, Solace, Kinesis, whatever, right? And you may have like traditional file-based sources, HDFS files, FTP or S3 or so on. And then you have your processing engines that basically read data from these sources, do some processing, and then based on whatever business logic you want, and then the outputs that are generated, they store them either in traditional data stores or they may send them out to visualization. So Apex comes in there. So it's the engine that will basically run your business logic to basically ingest and process this data, and eventually store the data in whichever destination that you want to do. Traditionally, if you're building a traditional type application, which is a backend application, you basically store the data first and then build your visualization on top of that. But some of the features we provide in DataTorrent is you can visualize this data in real time even before it hits a persistent store. Okay, and I'll cover that briefly later on. So why is stream processing? What are the characteristics of stream processing? Why is it different? Right? First of all, you need to have the capability of ingesting from a wide variety of sources. Streaming is new. There are still no established ways of sources. So you have Kafka is popular, but there are other messaging systems. You still have the traditional files in the mix. You may also have data in databases that you need to read in. So it needs to be able to handle all these kinds of input sources. Second, streaming is unbounded, which poses the biggest problem, right? So when you're doing batch processing, you start and you end. So it's ephemeral, right? You run for a certain amount of time, and then you're done. But with streaming, you could be running continuously and never shutting down. So think of that, right? So if you have a state that's growing indefinitely, your program's going to run out of memory. If something happens in your cluster and there's a malfunction and some node shuts down, your application cannot restart from the beginning, right? Because new data is coming in all the time. So your streaming platform or the engine that you choose to build your application on should be resilient and should be able to handle these scenarios. Second, you should be able to handle both process time and event time. So process time is essentially when you're processing the data, you may want to periodically look at the outputs, right? So because it's continuous streaming data, they may not, the end may be somewhere in the future or no end at all, but you periodically want some results out. So you need to be able to, the engine needs to have those semantics to be able to, for you to be able to publish those outputs periodically. Same time, event time is very important as well. So based on, you may want to do some analytics based on when the event was actually generated, group events by the timestamp when they were actually generated. And as I mentioned earlier, a lot of these operations that you're doing may have state in them. So you may be computing aggregates, you may be doing some rules, and all these things have memory. So even if there's a failure event, we need to be able to restore that and continue. And just like the input, your output also you may have various destinations, and the platform that you're using needs to be able to give you the flexibility to write to these different output sinks. Right. So this is what we strive to solve in Apex. So it's a streaming focused engine. That's what we built it from the scratch. So it's inherently distributed in-memory processing. So your logic is actually running distributedly on the cluster, and it's taking advantage of all the computational resources available in your cluster. It supports a simple Java-based programming model. So if you know core Java, right, basic Java, that's all you need to get going on Apex and build your applications. It provides scalability and fault tolerance out of the box. So if your data loads, if you have a large amount of data you're processing, no problem. It can scale your application accordingly. And also comes with a large productivity library of what we call operators. So operators are pieces of logic that you embed in your application. So for example, if you want to read from a message bus or you want to write to files, you don't have to write the code from scratch. There's already existing code that you can just plug in. And on top of it, DataTorrent provides an enterprise edition of the software where it provides a whole bunch of tools around monitoring, prototyping, and visualization, which I'll briefly cover later on. So here's how the stack looks like. So all we need is Hadoop. That's what we say. So underneath, you can use any major distribution of Hadoop. You can be on dedicated infrastructure or virtual. You can be on-prem or cloud. And then on top of it is basically Apex runs on Apex engine runs on top of that. And then you have the library of operators that you can readily use in your application. We also support a high-level API for folks who are not necessarily big data engineers, who basically want to get the ground running. We provide some of these commonly needed common use cases. We expose them as a high-level API that you can use. We also support batch, so essentially you can run your batch applications as stream. And of late, we also have these application templates that we have published that basically cover the common patterns, right? If you're going to do HDFS to HDFS replication or read from Kafka right to HDFS, we have a ready-made app that you can use. And of course, on top, DataTorrent provides different kinds of productivity tools, whether it's the rapid prototyping with the GUI assembly, the management monitoring, data visualization, and we also have some vertical-specific pipelines that we build. So with that, I'll start a deep dive into Apex. I'll probably move a little quickly because we started late. What's the basic programming model? So the basic programming model, when you use the Compositional API, is actually a DAG. So it's a graph of operators. So you take your big problem that you have, you conceptually break it down into these smaller logical functions. These are called operators, and you basically code each of these functions. You don't have to write code for each and every one of them. You can use the existing ones from the library that match your functionality, and then you write the new ones, and then put them all together as a graph and launch them. The important things to note here are it's a pure streaming. It'll be a pure streaming app. So as each operator is emitting a piece of data, the engine will try to get it to the next operator as soon as possible. There is no artificial batching, right, done by the engine. So you can get really low end-to-end latencies. So each piece of data we call a tuple, and it can be anything, right? It could be simple things like integers or strings, or it could be any complex objects. You could have complex JSON objects that you're sending across as well. And for each of these operators, you actually see a three-dimensional view, boxes in three-dimensional view. That is just to signify that you can have scalability. So each of this piece of logic can actually be running as multiple processes and dividing the processing of the data amongst themselves. So this shows the runtime view. As you can see, there's some the green boxes could be an application that you built on Apex, and it will run alongside any other Hadoop application you have, so it won't interfere with them. So in this case, if you have other MapReduce applications running, not a problem. Apex will basically run. You don't have to dedicate a cluster for the Apex application. And you can see these the numbers 1 to 6 are 6 operators in your application. It's just a hypothetical application. And these operators can be distributed as separate processes, or they can even be threads within the same process as 4 and 6 are. So you get all this configurability, right, how you want to lay down your operators. By default, the platform chooses same defaults. And then you have the tools to launch the application and monitor the application. With Apex, you have the CLI. With DataTorrent, you have the UI console, and we have some specific talks later on where our engineers will go deep dive into those components. And you basically install Apex or DataTorrent only on one node. You just need to install it on one edge node or a node in the cluster, and then you basically launch your app from there, and then it just spreads onto your cluster. So let's say you want to build an application. What does it entail, right? So we have various ways for you to build an application. The primary way is you write code in Java. Even within Java, we have different options. So you have the Compositional API, which is the low-level API. So essentially, you are writing these operators, connecting them together. We also have a high-level API for the commonly used patterns. So if you're reading from Kafka, doing some flat map, doing some counts, doing some windowing, storing data somewhere, those kinds of patterns are covered. And we keep augmenting the high-level API from time to time as we see common usages of our common patterns. And we also have a runner in Beam. So if you use Beam as well, you can use Apex that way as well. Then some of the non-traditional programming ways are, if you use CalCite with Stream SQL, we support that. We also have a JSON if you want to basically wire up the operators. So you basically still have to have the operators, but you want to wire them up with a JSON property file. You can do that. So that could be driven from a UI, which is what our UI does. There's also a property file way of wiring up the DAG. And we also have coming up with a Python API for the high-level bindings. That's work in progress. Should be released soon. So when you're building this application, the first thing you do is you take your application logic, break it into these logical components. Then you can go look into the library to see if there are any existing operators, choose them, and then develop the new ones, put them together, build the application, launch it, run it, monitor it, debug it, go back. If you find any problems, go back and fix it and iterate, basically, right? And the tools we provide at DataTorrent make that life easier. So to illustrate it, let's look at a sample application here, which is a very common pattern. You're reading from some message queue, writing to a database. So you can conceptually, one way to break this is you may have these 5 steps. You're reading, this is a sample word count. So you're reading line by line from Kafka. You're parsing the line, breaking it into words. You may be dropping the commonly occurring words. And then you're counting how many times each word occurs, and you're storing the output into a database. So these could be 5 operators, right? So here's a high-level API way of doing it. You create a stream. You specify that you want to read from Kafka. You specify the brokers, topic, the strategy. Then you specify the parsing function, the filter function, saying I want to drop these commonly occurring words. Then you apply a window. It's one global window because you're just going to have one big count. And you're basically going to update the count every 1 second. So that's the trigger firing of 1 second. And you basically want to keep accumulating the count. So you want the count to keep growing. It's a cumulative count. And then you're saying count by the key. Let's count by the words, and then print the output, right? So it's very simple. Suppose you want to do the same thing with the compositional API. This is what it looked like. So you create each of those individual operators. So you're creating the Kafka operator, the parser, the filter, the counter, and the JDBC output, and then you're connecting them up. You're connecting the Kafka output to the parser input, parser output to the filter input, so on, right? So in fact, the high-level API will eventually decompose to this underneath. Right? So let's say you are trying to go and build this application. First, you look at what are the available operators in the library. So this graphic shows all the like a high-level classification of the different operators that are available in the library. So we have the traditional database operators, file operators, the NoSQL databases, message queues, parsers. All these are readily available. And Malhar is also part of Apex, as you know, right? So this library is always growing, and we're adding new operators as well. And we basically have a rigorous testing for these operators. So we basically want to make sure that these operators are production ready. So we test them not just for functionality, but for scaling, for make sure it's idempotent, fault tolerant, and all that. It performs under load. So just specifically look into 1 or 2 operators. So the Kafka input is a commonly used operator. So in this case, our Kafka input operator actually understands the structure of the Kafka topic on the Kafka side. So, for example, if you have multiple partitions for a topic, it will actually dynamically create multiple partitions on the Apex side, so that you have multiple readers reading parallelly from the different Kafka partitions. So you're basically able to read data at the maximum throughput. We also have one-to-n strategy, where actually one partition is reading from multiple Kafka partitions. And then it's fault tolerant, idempotent, and all that, so you can get exactly one's behavior even in case of failure scenarios. And one more new message bus we're working on is Solace, and there's a pull request for that, you can follow that as well. So if you want to write an operator on your own, what would it look like? So here's a very simple operator. So here, this is the filter operator where you want to drop the commonly occurring words, like articles, right? A, an, and the. So essentially, to do that, you write a Java class, you extend this base operator, which is part of the API, and then you define, to receive data, you define an input port. To send data out, you define an output port. And you basically specify a type for the input port, which is strings. So essentially, you're saying I'm expecting strings, which is basically you're going to get lines from the Kafka, from the previous operator, which is going to be the Kafka operator. So as soon as a piece of data arrives, the process method is called with that particular string. So you can do whatever you want at this point. So in this case, I'm basically checking if this string belongs to, is one of those 3 words. If so, I'm not going to do anything. If it is not, I'm then going to emit it. So by not doing anything, I'm actually dropping the data. But by actually, if it's not one of these, I'm going to send it down to the next operator. Right? So as you can see, it's a fairly simple programming model. So next, let's look at some of the features of Apex. So one of them is scalability. So let's say you build this DAG, this application out with all these operators. In this case, let's say you have a DAG of 4 operators, 0, 1, 2, and 3. So so from programming engineering, this thing, we number things from 0, right? So each stage, you can actually have multiple processes, right? So for example, in this case, stage 1 and stage 2 have more than one process for it. Stage 1 has 3 processes, stage 2 has 2. So the reason is stage 1 may be doing some heavier processing than stage 0, so actually it needs multiple processes to handle the amount of data that's being read in from stage 0. So you can independently partition each of these stages, right? And then the engine also automatically inserts what are called unifiers in between. So unifiers are a way of aggregating the outputs, right? So for example, if your stage 1 is actually calculating a sum, right? So now because you partition and you actually you have multiple processes, each with substreams of data, they all have partial sums. So their result may need to be combined to get the final sum before passing it to the next stage. So unifiers do that job. And we support some other advanced partitioning mechanisms like parallel partitioning. So in this case, when you have successive stages operating on each piece of data independently and there's no shuffle required, so you can do that. So as you can see, stage 1, 2, and 3 in the picture below. I don't know if I have a, okay, I don't have a, okay. Yeah, in this case, you can see that the same number of partitions in successive stages, and there's no shuffle required. And the last one is cascade unification. So essentially, if you have a lot of partitions, and think about hundreds of partitions here, you may not be able to bring all the output into a single operator or a single process because there's so much data to bring in. So you can then aggregate in stages. So essentially, here there's 2 unifiers in the first stage and then 1 unifier in the last stage. So these guys are computing the partial aggregates, and the results are coming to the last one. So this could actually extend to multiple stages. Okay, and then dynamic scaling is another unique feature of Apex. Essentially, typically in big data or streaming data, you can have your data flow. You may not know or your data flow might change at different points of time during the day. You may have a peak data flow, and you may have a smaller data flow at the rest of the time. You don't want to provision for the worst case, right? You don't want to basically create all these partitions just waiting for the worst case. So you can have your application, your operator scale up and down. So you basically start with a small number of partitions, and then when the load increases, it can dynamically increase. All this can happen without losing any data and preserving state. So we have an API. So if you have stateful operators and they're dynamically partitioning from a small number to a large number or vice versa, we have a way for you to distribute the existing state. And one of the examples of dynamic partitioning is the Kafka operator, right? It determines how many partitions are there for a topic on the Kafka side and dynamically creates the same number of partitions if you're using the one-to-one strategy. So how do you customize your application? So you built out your application in Java, you want to launch it, but sometimes you basically don't want to hard code different things, like you don't hard code your database location or your Kafka topic and so on. So you can specify them with properties. Another thing you can do with properties is you can specify you can control the platform features. So for example, you can specify your scaling. So in this case, I'm saying for the parser, I just want to use, I'm sorry. Let me see if I can, okay. So in this case, I'm saying I want actually 4 partitions for my parser, and then I'm saying that filter and counter need to be parallel partition. So you can specify these things also as attributes, as properties, along with your business properties that are specific to your operator. So the resultant application, when it's running, might look like this. So in this case, the input are the Kafka operators. So assume that in this example, the Kafka topic had 2 partitions, and I was using one-to-one partitioning strategy. So there are 2 partitions here. We specified 4 parsers, and we said filter and counter are parallel partitions. So you can see there's 4 partitions of each. And then there are the unifiers that were inserted by the platform in between because we went from 2 to 4. And the counter, there was no partitioning. So all the the counter had 4 partitions, but the output has no partitioning. So all the results came to a single unifier onto the output, and the output's writing to some output store. Right. So next, let's look quickly at checkpointing. So fault tolerance is the other important thing. So essentially, as I said, when your streaming application is running for a long time, if there are failures, there's no notion of you can't start from the beginning, or basically you cannot just restart because your results will be wrong. So the engine provides a way for you to recover for the application to recover automatically and without losing state. It does this by many different mechanisms, but the core is that there's a checkpointing mechanism. So every operator in your DAG, in your application, the state of it is checkpointed to a persistent store. By state, I mean anything that you have in your memory. It's not data, but it could be any aggregates or any other computations that you're performing. So those things are saved periodically, and then whenever there's a failure event, then the engine will restore that operator to the previous checkpoint and the downstream ones as well, so that everything can recover correctly and process the data without any loss or wrong calculations. So another unique feature we support is incremental recovery. So if a particular operator in the middle of your application, let's say you have a DAG of 5 applications and the third operator goes down, you don't have to restart the entire DAG won't be restarted, right? Only the third operator and the fourth and fifth will basically recover. 1 and 2 will continue as if nothing happened. So the reason we do this is possible is we have an internal buffering mechanism that's a progressive buffer. So actually, when an operator goes down, it just pulls the old data from the previous upstream. And when all the operators have moved forward, that data is being periodically purged. So these buffers are not growing indefinitely. And we have some detailed talks on it later on that you can attend. And end-to-end exactly once is another thing that's very important to us. So what is end-to-end exactly once is, the way it's defined is, if you have an application, even in case of failures, you don't want any loss of data or duplicates of data in the external system. So let's say you're writing to an external system like a database or files or any other store. You don't want to see any data missed or duplicates in the external system, even in case of failures, or node failures or operator failures. So we handle that. It's actually that is done as a combination of both the engine and the operator working together, and we have specific talks on that later on that you can attend and see how that is done. So I'll quickly go through some of the enterprise features we provide in DataTorrent. So this is our monitoring console. So you can see your application as it's running, all your different operators and your partitions, and you can get all the stats and the total resource usage and the main events and logs and all that right in this console. So you get a very detailed view. It's not like a black box. This is a real-time dashboard. So we have a rich set of widgets that you can use readily with your application to visualize your output or metrics. And then we also have a prototyping tool where you can actually, if your operators already built out, you need to build them in Java still. You can give this to an analyst who can drag and drop and connect these and launch his application from there. We also have an AppHub where we provide app templates that are basically can form as a basis for your application. So these have 3 or 4 operators connected for commonly used cases. You basically can take them, the code is available, and you can insert your specific business logic in between, and you may have a ready to go app, right? And we are basically always augmenting this AppHub, and we're adding new apps all the time. And I just want to end quickly with a couple of use cases where Apex is being used. One is at GE. So GE has built a cloud-based IoT platform called Predix, and where basically all the data from their GE machines or on the field, whether it's a windmill or a deep sea oil rig or a train or airplane engine, all this data is basically brought in for processing. So they're using Apex and DataTorrent underneath for their ingestion and ETL. So Capital One is the other place which basically used Apex and DataTorrent to analyze their credit card transactions. So in swipe, so when you swipe your card, they basically want to analyze whether the transaction is a fraudulent transaction or not. So they basically ran a POC, and they were trying to, I think, get 20 milliseconds, but end-to-end latency, but they actually ended up with 2 millisecond latency, which satisfied their requirements by a big margin. Okay, so that's all I have. Thank you.